so the first half of this lecture, we're going to learn Kirchhoff's laws. We're going to work on setting up the experiment for this afternoon. Second half will be magnetism, which we'll study for the next couple of days. There's a story time with Dr. Eschenberg. First, I've taught this one subject for a long time. How long? So long it's rude to ask. 2, I'm the best. It's not bragging, it's truth. What I have done is I have studied this problem and studied you guys. Not physical science students, not Cal-based students, not physics majors or physics grad students, pre-med, pre-pharm, exercise science, general physics students. I have polished this. I have made it so straightforward, it works. Now, with vectors, what was the thing about vectors? We had the vector butterfly. I told you we're going to do it by the reference angle method. It was a very strict system that had rules. And there were other things where circular motion, torque, and all that stuff, where I just kind of said, and it frustrated you, and it made me so happy to hear your frustration, that you could just kind of freestyle it and piece stuff together. With Kirchhoff's laws, this is my response to hearing you guys say, just tell me what to do. For the next hour, if you do what I tell you to do, Kirchhoff's law will not be a problem. It's going to show up on the test. It's going to show up this afternoon. If you guys bomb it on the test, it'll show up on the final. It will be here. So this is how I teach it. Now, we're very familiar with the number line. And if I said that your velocity was less than 0, we know that that means that you're going to the left. And if I said your velocity was greater than 0, you're going to the right. That's easy, simple. Then the next step was to say, well, we're going to do Atwood's machines. And the way that the number line is set up, that up and to the left is negative, down and to the right is positive. This is basically taking this number line system, cracking it in half, and then just bending it. And you hear me call it the loopy-droopy number line. What we're doing now is we're taking this line and completing the transition and what I'm going to do is I'm going to call that J. And J is my word for current velocity. Now, technically, it's not correct, but it gets the job done. So if J is greater than 0, I is clockwise. If the J is negative, the I is counterclockwise. And the way that I generally think of the relationship between I and J is I is equal to the absolute value of J. Now, there are many ways to teach this problem. I've narrowed it down to one. It's because I think it's the most efficient, it has the fewest moving parts, it's the most easily understood, and it is very rigid in the way that you do these problems. So J is my current velocity, I is what I think of standard current And to use an analogy from 213, I think of it as current speed. But if you just want to say current, that's fine. I'm just using this way as teaching it in a way that makes it easier. There are many different ways to do this. You may have friends who are electrical engineers or people at other institutions, or you read it off a bathroom wall on how to do this. If you do it the other way and get it right, I'm very happy for you. If you do it a different way and you get it wrong, you're gonna get crushed. Because what I've tried to do is teach this in the most efficient way possible. So I'm just letting you know. Really what I'm telling you is just follow the path and the velociraptors won't eat your face. A lot of people come back with no face and they tell me that they jumped in the velociraptor pit. That's what you get. The problem itself, when you see something look like this, now, the order of the, or the placement of the batteries is kind of random. It could be all sorts of ways. And the way that we typically label them is you have V1, R1, R2, R3. The resistors tend to go from left to right, R4 and R5. For something like this, we do not use a ground. The ground doesn't really matter, and we're going to get to that in a little bit. And so you have an assortment of resistors. The TAs and other teachers try to make it too complex. And you'll see these weird things, like they'll put, like they want to know, like this big I2, and they want to know what that is. For the moment, ignore it. You will be given, in fact, I've got the worksheet. In fact, what we're going to do, I'm going to set this up in general form, and then I'll do that problem. Well, actually, we'll set it up generally. And then what I'm going to do is do an example, and then I'm going to do that example, which is in the lab for this afternoon. When you see a problem like this, and all of these resistors are, hold on, I gotta think of some good values. R3 is 15 ohms, R2 is 9 ohms, R1 is 6 ohms, R4 is 10 ohms, and R5 is 20 ohms. V1 is 27 volts. V2 is, hold on. Let's make it 40 volts. So I've given you all these resistor values, I've given you the two batteries, and really the big question is, this is going to be the question asked on the test. What is the current and direction of current, or current magnitude, and direction of current passing through R3. Now, the important thing for Coulomb's law is we're talking about the resistance or the current passing through the middle resistor. What they're going to try to do is they're going to ask all these questions about what's the current flowing through R2, R5, V2, R4, all that nonsense. That's fine. That's a lab. You got a whole 2 hours just playing with this stuff. On the test, it will be simply, given this arrangement, give me the current magnitude flowing through the middle resistor. And is it down to top or top to bottom? So I want, really, an example would be the answer is 2 amps up or 1/2 amp down. So when you see all these weird capital I's and they want to know the currents going through the ammeter and all that garbage and all that nonsense, focus on doing one thing. Find J1 and J2. And as I've said before, J1 and J2 can be positive or negative in the way that we set this thing up. Positive means the current flows clockwise. Negative means the current flows counterclockwise. Now, what we're going to do is we're going to use something called the loop rule, or loop rules. And really, they're kind of Kirchhoff's rules. There is something called the node rule, but in the way that I do it, in my simplified manner, I don't even use it. We'll get to the node rule when we talk about this stuff over here. For the loop rules, what you do is you set up a loop. And what we're going to do as an example, R1, R2, R3, and V1. And this is loop 1. And then you have the other loop. What you do is you look at each of the blocks and you make a loop. And you say that you then build one equation per loop by walking around each loop. We're going to build an equation for each of these loops. Now over here, the loop looks like that. Over here, the loop looks like that. So this is loop 1, and then this is loop 2. We'll only be doing 2 loops for these types of problems. If I was doing Cal-based physics, I could do 3 or 4 and we'd have so much fun. But we're not. It's going to be dull. Just 2. And you're going to build these equations, and these loops follow one I hate saying simple because a lot of people just go, that's not simple. One observation. That the delta V for the loop is 0. So in English, what I'm talking about is, well, first off, hold on. I know she's going to watch this video. The person who sits right there is not here. And that upsets me, Amy. All right. You know what? She thinks I don't like her. She's right. So, now. So each of these loops, if you walk the loop, the change in potential is 0. And so what I'm going to briefly do is walk around the room, and we're going to go, well, obviously. Along that path is a battery. Along the back of the wall is a resistor. There's another resistor over there. There's a resistor right here. So if I start there and I go up that side of the room, I go across the battery and there's a change in potential. And I walk from there to there, and even though it looks like there's a slight change in altitude, so there's a change in potential from there to there. And there's another change in potential from there to there, and from there to there. Let's ignore the fact that the floor is flat and there's no change in potential. But the important thing is, what's the total change in height if I start here, walk to the back of the room, walk over there, walk down there, and walk back here? What's the change in height? 0. So for each of these loops, if you start at one point and you walk around the whole loop, the change in potential is 0. And that's what we're going to do for each of these. The change in potential for loop 1 is 0. The change in potential for loop 2 is 0. And for all the sleepy people in the room, it could be worse. We could have class at 8. That sucks. Let's just try to be happy about it. So now, what we do is we take the number lines for J1 and J2 and we kind of draw the currents out. This is kind of like the J1 number line, and this is the J2 number line. So they're number lines that have been bent completely in a circle. So if you find that the value J1 is negative, then you know the current is actually running clockwise. So the initial guess is we're setting these things up so that the loop we walk is the same direction as the current, how should we say it? The number line, the direction. And so we put these in a clockwise formation as well. When you go through each of the loops, when walking through the loops, there are 4 different scenarios that can happen. And in all of these, the loop, or in all of these motions, we're going from left to right. I want to know the change in potential when we go from left to right. Now, in these two, the current, you have the option of the current either goes to the right or the current goes to the left. In the battery, it is not important. There was a question, oops, not you. There was a question that said, you go against the current through a battery. What's the change in potential? And the answer is there's insufficient information, because the important thing about going through a battery is, and its change in potential is, are you going from the negative to the positive lead or positive to negative? In the case of the negative to the positive lead, your change in potential is positive V, whatever that potential strength of the battery. From positive to negative, the delta V is equal to negative V. So it's not the direction of current that's important when determining change in potential through a battery. All that matters is from what pole to what pole am I going? When you're going with the current across a resistor, the change in potential is negative IR. When going against the current, the change in potential is positive IR. This is a lot like going, if you go down a waterfall, your change in potential is negative because you're going downhill. When you're going against the current, you're going upstream, you're reaching a higher potential, and so the change in potential is positive IR. And so these are some of the fundamental rules behind Kirchhoff's law, that there's a change in potential when you go from one end to another end of either a battery or a resistor. The other thing that we notice that with these Kirchhoff's law problems is that there is no ground. Having a ground in this type of problem is unnecessary. And why is that? Because I don't care what potential it is. I don't care where the ground is, what's the reference point. All that I care about is that the change in potential for the loop is 0. There is only one part that is stranger than the rest. That is moving through the middle resistor. Now that middle resistor gets a little bit tricky, and the thing that you have to remember is I drew these two loops separately because I wanted to illustrate more to the point of the loop and you moving through the loop. But the one thing that we really need to remember is that the current in the middle, you've got a J1 coming down and a J2 coming up. So when you go from this point to that point, when you're going through that middle resistor, R3, you have a current J1 going down and a current J2 coming up. So if that is A and that is B, the change in potential from A to B is J2 R3 minus J1 R3. Because when you're going from there to there, you're going against current J2, which is the current times the resistance, or in this case, J2 and R3. And then you're going with J1, so that's J1 R3. If your change in potential across that middle resistor is from B to A, it's J1 R3 minus J2 R3. So that's only the middle part that you have to worry about. For any of these other resistors, other than the middle, it's simple. You just follow these. It's just the middle one that gets a little bit weird. Now, what I'm going to do first is we're going to walk loop 1. Why do I do it? Just to be consistent. I always start in the lower left-hand corner because that's just how I do it. You're perfectly allowed to do upper left, upper right, lower right. I just try to be consistent. In loop 1, I go from there to there with J1. So what happens is I'm going with J1 across R1. So it's minus J1 R1. Then I go from there to there with J1, so minus J1 across R2. Now I go from there to there, which means I'm going with J1 or minus J1 R3, but against J2, positive J2 R3. And then the last bit, I go from there to there. I'm going from a positive to a negative lead of battery V1, which means I go minus V1. That's a complete loop. So for loop 1, I've set up the equations and it's all equal to 0. Now I'm going to set up loop 2. So for loop 2, start in the left-hand corner and I go with J2 across R3. So minus J2 R3. And I'm going against J1 across R3, so that's plus J1 R3. I go from there to there, which means I have minus V2. I go with J2 across R5, so minus J2 R5. And if I go from there to there, it's minus J2 R4. And so those are all the steps for loop 1 and loop 2. At this particular point, we know all of the R's and V's. I don't know J1 and J2. Kirchhoff's law's problems at its core are 2 equations, 2 unknowns. And it always makes me happy to think about that Twitter or that tweet where one lady said every time Dr. Eschenberg says 2 equations, 2 unknowns, I die a little more inside. And it's not that bad. This is how you do this. I'm going to rearrange the J1, factor out the J1s so that it is minus J1 R1 plus R2 plus R3 plus J2 R3 minus V1. Down here I'm going to factor out the J2s. So R3, R5, and R4. I'm factoring out the negative J2 and negative J1. And then I go plus J1, R3, minus V2. It's at this point where we finally see Dr. Eschenberg say, okay, fine. This is the perfect opportunity to plug and chug. And I'll do it, and I'll tell you why. This is negative J1 R1. Where's my thing? All right. R1 6 9 15 R3 15 J2 V1 is 27. Now what I do is I compress this. 9 plus 6 is 15. 15 plus 15 is 30. Minus 30 J1 plus 15 J2 minus 27. This becomes minus J2 R3 15 R5 20 R4 10 R3 15 minus V2, which is 40. This simplifies to 15, 20 is 35, or yeah, 35, 45, so minus 45 J2, 15 J1 minus 40. Had I simply given you those two equations and I said, those are the two equations, give me the two unknowns, you could go, oh, that's easy. It's one of the reasons why I think it's a lot easier to plug in the values specifically at that point so that you could just simply look at this and simplify it. And it goes a lot faster. The other thing that, another reason why I do what I do is when you look at this, I am like you. I'm lazy. I like to think of it as efficient. I'm really more interested in the understanding the physics and setting the problem up and getting it all straightened out. The numbers are secondary to me, and what I typically do is I add a layer that if you see it, you could actually make it more easy. In the test problem, it'll be set up like this. What number is all of these three divisible by? 3. So I'm going to divide both sides by 3. Negative 10 J1 plus 5 J2 minus 9. So really what I'm doing is I'm simplifying the equation to make it a little bit more easy to handle. All of those three are divisible by what? The largest number that you could divide these by. 5. And once again, yes, you gave the right answer. No, you gave the wrong attitude. It should be 5. I would even appreciate it had, now I'm curious, what are you going to be? Yes, you. A doctor. You don't want that. I want a doctor who says, look, we have an issue, we're going to be able to work through this. Remember this lesson right now. Because I'm going to tell you, you're going to go to med school, and there's going to be a lot. I need you to be a little bit more confident. Don't you want your doctor to be more confident? That's something that you like in your doctor. Yes. Now, in fact, had you said, you know what, these are divisible by elephant. Can't you see? Divide by elephant. All fine. I appreciate the correct answer. Okay. So what's the answer? It's 5. We'll work on it. Don't worry, I'll be back. So these are divisible by 5. And so now those two equations are even more easier, or you're able to handle those more easily. And what I'm going to do is I'm going to take one of the equations, solve for one of the variables. Which equation, which variable? I don't know. I just pick. First equation, solve for J1. Why? I don't know. So 5J2 minus 9 equals 10J1. Or 5J2 minus 9 divided by 10 is J1. I'm going to take that value and slap it into J2. So now, as you can see, it's another easy... What I did one time, only takes once to appreciate it, is I kept the variables and all their letters, and I solved for J1 and J2. The algebra is atrocious. So I solved Kirchhoff's law in general, which is horrendous. This is why I plug the numbers in. For you guys, I want you to plug the numbers in. It makes things go more smoothly. Take that, plug it in there. 0, negative 9J2 plus 3. 5J2 minus 9 over 10 minus 8. Now we have an equation that only has one unknown. We can now solve for it. Oh, it's a big ton of garbage right now. What I would do first to get rid of the denominator, I'd multiply everything by 10. So this gives me negative 90J2 plus 3, 5J2 minus 9 minus 80. So multiplying everything by 10 will get rid of that. I'm going to distribute the 3 and we get this. Now I'm going to bring in, mix my J2s and my numbers. This gives me minus 75 J2. This is minus 107. 75 J2 is equal to minus 107, and J2 is equal to minus 107, 75. I don't think we can simplify this. Let's find out. 107 divided by 75. Yep, that's as low as you can get. To give a final answer, J2 is negative 1.43 amps and I2 is 1.43 amps counterclockwise. And that's the value of J2 and I2. That's one of the unknown. When you give me the final answers, I'm fine with you giving it as a decimal to those many places. But when you're dealing with the numbers inside the problem, keep it as a fraction when you're plugging it back into the J1 equation. So this becomes 5 minus 107, 75 minus 9 divided by 10 is equal to J1. And that nonsense gives me a J1, which is minus 1.613 repeating amps, or you could say, or I'm sorry, yeah. So I1 J1 also in a fraction is minus 121 over 75, and I1 is 1.61 clockwise. Or I'm sorry, I take it back, counterclockwise. So now we have the answers. Both are counterclockwise. And for all of these Kirchhoff's law problems, the laws are set up the same way. You set it up as a two equation, two unknown problem. The goal is to get J1 and J2. And now that you have J1 and J2, things get a lot easier. There are only 4 combinations for J1 and J2. So J1 can either be positive or negative. J2 can only be positive or negative. For J1, that'll be the first symbol. For J2, it will be the second symbol. And what I like to do is I like to draw my current. So positive is clockwise, and when it's on the left, I write it like this. Minus is counterclockwise, and I like to write these on the left. For positive on the right, it still needs to be clockwise, but the way that I draw it is I draw it like that. And for the negative, it is counterclockwise, so I draw it like that. You can look at these and see the following. They're against, in the case, oh, that's horrible writing. Against, width, and width. So there are only 4, positive, positive, negative, negative, positive, negative, negative, positive. Positive, negative, positive, negative, or I'm sorry, positive, negative, negative, positive. Where there is different signs in the J, it's easy. Add the I's to get magnitude. So in the case of, let's say we had J1 is equal to -2 and J2 is equal to +3. J2 is like this, J1 is like that. You look at this, the current flowing through the middle is definitely, without question, bottom to top. So all you do is the current in the middle, 2 + 3 is equal to 5. If you have it as a situation where J1 is equal to +2 and J2 is equal to -3, J2 looks like that, J1 looks like that. Current goes down. It has the same magnitude, 2 + 3. It doesn't matter. So if you see something where it has opposite signs, I dream about that. That's easy. Just add the magnitudes together, and then all you got to do is figure out if it's going from bottom to top or top to bottom. positive, positive, negative, negative requires a little thought. In the event of a positive, positive, or negative, negative, they're going head to head. So what you do is that current magnitude through the middle is equal to take the bigger one and subtract from it the smaller one. Because the one that's bigger determines direction. So in the example of J1 is equal to -3 and J2 is equal to -5, J1 is -3 like this, J2 is -5 like that. This is the bigger one. So the current goes top to bottom, which means that the current through the middle is equal to 5 minus 3, or 2 amps. In the event of J1 is equal to 3 and J2 is equal to 1, they're both positive, so they're both clockwise. J1 is the bigger than J2, so the current is going down, and I mid is the bigger one, 3, and you subtract from it 1, and you get 2 amps. And so those are the 4 possibilities. Now let's look at our problem. The problem had us with, I'll put this back up in just a second. I1 is 1.61 counterclockwise. I2 is 1.43 counterclockwise. And so we're left with both are counterclockwise. So they're both head to head. Which one is the bigger one, I1 or I2? I1. So this current is going to follow the direction of I1. And since this one goes from bottom to top for I1 in the middle, the current direction is from bottom to top. The magnitude of that I mid is 1.61 minus 1.43, or 0.18 amps. And it's 0.1 amps bottom to top. And that would be the final answer of the problem. So it does do a lot of, there are a lot of intricate things about it, but when you start thinking about it, it ends up becoming a lot, I mean, it's really, I wouldn't say easy, but once you understand, talking with, Chung has been with me for a year. He knows how I teach it. I taught it to Carlton yesterday, and he's aware of it. The procedure in the lab is a little bit different, but the first thing that I want you to do and since we're kind of running low on time, I'm going to skip it. You take the procedure that I gave you, you apply it to this one right here. You could do this before lab and figure it out and get the ballpark answers for I1 and I2. The ammeter over here, that gives you J1. The current ammeter over here, that gives you J2. The one in the middle is the combination. Yes?
So how do you know if it's counterclockwise or clockwise?
If J is greater than 0 or positive, I is clockwise. If J is less than 0 or negative, I is counterclockwise. And that's the reason why. It's all based on the sign of J1 and J2. The reason why I use J is for grad students, we can accept that I is negative. But what ends up happening for the students is if they do it where they use I instead of J and they end up with a negative I, they rework the entire problem and they end up getting it wrong. Like there's some weird motivation for them to just rework the problem from the beginning and start flipping signs because they know that I is now negative instead of positive. And if you start flipping this, most likely you're going to slip up and make a mistake. So that's why I do current velocity and current speed, and I's are the speeds and J's are the velocity. So that's Kirchhoff's law in 50 minutes. It's not that bad. Know how to do this on the while I'm about to start magnetism. Problem sets 4, 5, and 6 are on the table. You can pick that up. Problem set 4 is due 2 days from today. And today is what? Tuesday? Yeah. 4 is due Thursday, 5 is due Friday, 6 is due Monday. Of course, flexibility is allowed. Test 2 has been posted with solutions for one of the tests for the for the multiple choice. There's something called a test 2 bank file. In the old days, I used to do matching, and I ended it and replaced it with multiple choice. And it was basically after a student or one of my graders said, this is giving free points to the class. You got to do something about this. And so that's when I started doing multiple choice. There will not be matching on the test, but it'll give you a good idea of what problems will be on the test. This will be on the test. One of the problems will be, given this arrangement of resistors and batteries, give me the current flowing through the middle resistor. Is it going from bottom to top, top down? That's it. That's the problem. And so that is that. All right. Any other questions before we move on? Okay. Let's see.
Can you show how you walk around the loop one more time?
Okay. In fact, what I'll do is I'm going to use this as I'm going to walk the loop through these. So there are 2 loops here. I would ignore, well, in the way that they have set up capital I1 and capital I2, those are our J1s and J2s because they're both clockwise. The other thing, while we're talking about this, You don't have to do this step, but I'm going to show you. When I look at this, I look at the batteries, and this gives me a ballpark idea of what my J's should be in terms of sign. It's not a guarantee, but it's a good bet. This battery causes the current to flow in a clockwise direction. So I would not be surprised if J1 is positive. I could put a huge battery over here and it would overwhelm that and I would get a negative answer. But most of the time it ends up being positive. This one causes the current to flow in that direction, so I would not be surprised if J2 is negative. It could be positive, but for the most part it will be negative. So if I get a positive J1 and a negative J2, I'm good to go. Loop 1 is me walking like that. Loop 2 is me walking like that. There are 4 parts in each of these. There are these 2 resistors, that battery, and the middle resistor, which is the tricky one. Same for loop 2. So what I'm going to do now is I'm going to walk the loops. When I walk the loops, I always walk clockwise with J1 and J2, and I always start from the lower left-hand corner. Lower left-hand corner, you could start at any other corners, but I always pick lower left. The main requirement is when you walk the loop, you gotta finish the loop. The starting location and the ending location have to be the same thing. Otherwise, you can't say that delta V1 is equal to 0. Can't be done. But in this case, we will walk the loop. I'm going from negative to positive across battery 1. Now they use epsilon, and I'm fine with that. I tend to write it V1 and V2. So this is negative to positive across V1, so this is positive V1. I'm going from there to there with J1 across R1. So it is minus J1 R1. There is no J2 flowing through R1, so I could ignore J2 at the moment. I go from there to there. That is with J1, because I'm going from top to down with that current, but I'm also going against J2 across R2. So it's positive J2 R2. And then the last bit of the walk is from there to there, minus J1 R3. I walk across an R3 resistor. I walk with J2, so it's got, or I'm sorry, J1, so it's minus J1 R3. That's one of the loops. Question.
So it's positive when you go against the J?
When you go against the current, it's positive, like I mentioned earlier. Going against the current is like going upstream. You're increasing altitude, you're increasing potential. So you're increasing from J2 going from there to there, but you're decreasing with J1 going from there to there. For loop 2, I start there. I go from there to there with J2 but against J1. So delta V2, which is equal to 0, is equal to minus J2 R3 plus J1 R3. I'm going from there to there against J1 but with J2. With J2 against J1. I'm going from there to there. I'm going from the positive to negative end of the battery. So minus V2. Here I was going from negative to positive. positive. Here I'm going from positive to negative, negative. I go through R4, so minus J2 R4, there to there, and then R5 minus J2 R5. And that's the setup for both the loops. Now it's just a question of two equations, two unknowns. Solve for J1, take that J1, plug it in the other equation, get a numerical answer for J2, plug that in back into the first equation. Now you got numbers for both. Now that you got numbers for both, most likely J1 is positive and J2 is negative. If that's the case, it's awesome, because most likely you're going to get a situation like that. The currents are combining from top down. I wouldn't be surprised if this is I1 plus I2 down as the answer. This one measures that one will measure J1, that will measure J2, that one will measure the current flowing through the middle resistor. And what I would do is I would take these resistor values here, plug it into these guys, and then I would have a good idea as to what numbers I should be getting anyway in the lab. And I mean, there's no need to do this calculation at 1 o'clock or 3 o'clock. You could do it before lab, easy, and have a good idea. It's a lot like I told you how to figure out the positions on the pipe for the speed of sound in air, where to find the resonances, because you just kind of do it, kind of rough guess it, and you can figure it out. It's the same thing with this. And so that's how you form your boxes, or your loops, your loops. All right, anything else before we go to magnetism? All righty. Now what I'm going to do, I'm going to look at the problem set real quick. And what may end up happening, the way that the problem sets are set up, I mean, like I care about this stuff being turned in on time. These problem sets were done in the spring. They're on video. The solutions are already out there. But I want you guys to get done so that you don't fall behind. These problems, for problem set 4, turn them in as a group. So if you have to turn, the grader threw a fit because I took the second page of problem set 2 and put it onto problem set 3 and he went nuts. So we're not going to split up the problem sets this time. So, but problem set 4, you're ready to do problems 1, 2, and 3. And what we're going to do in the next 49 minutes is to get ready for, oh goodness, a lot. Okay. The first thing that we're going to do is current in a wire creates B fields. Now, B field is magnetic. Just as E is electric, B is magnetic. Now, one of the interesting questions is, why is B magnetic? Because if we look at it, I asked the same question about impulse. Not impulse, momentum. Why is momentum P? There's no P in momentum. But momentum in Latin is impetus. And that P in impetus is the P that they use for, and it's related to impulse. And that's where they get the momentum. For the B, we all just blame, there's this one professor, and he wrote 5 equations, and the magnetic equation, or the magnetic field, was the second equation that he wrote. So he was just going, A was the first one, B was the second one, E was the 5th one, and he got lucky, and electric field was E. B is magnetic because it was the second equation that he was writing down in his publication. So B is magnetic field. The unit is Tesla, or T, after the early 20th, or late 19th, definitely early 20th century scientist, Nikola Tesla. Just ballpark figures, typical B field strength is on the order of millitesla up to maybe like half a Tesla. That's the typical B field strength. The largest magnetic field created by humankind is on the order of like 7 Tesla. So if someone says, "Oh, we got a magnet, it's got a 50 Tesla magnetic field," don't believe it, because that's not. Unless it's made out of rebellium, and rebellium can do anything. But typically, I'm going to try to keep the numbers on the order of microtesla, millitesla, stuff like that. In what we're going to look at is how to do problem 8 and 5. And that is, current in a wire creates magnetic field. There are 2 major classes of wire. You have the straight wire, and then you have the arc. Straight wire, it's just straight. The arc is, you have a length of wire that's all at the same distance from this point. With an arc, the only easily measured point in the system is the B field at the center of the arc. And the B field at the center is mu naught I theta over 4 pi r. Mu naught is a constant. Mu naught is something that I've never really bothered to memorize. I think it is, 4 pi times 10 to the negative 7. Oh my goodness, I've actually memorized it. 4 pi times 10 to the negative 7 with a whole bunch of units behind it. I is the current. And theta is, and this is one of the few occasions where theta is the arc in radians, not degrees. So these arcs all have to be based on pi. A full circle, pi. Semicircle, or I'm sorry, full circle 2 pi, semicircle pi, quarter circle pi over 2, etc. For a straight wire, it could be left or right, it could be at any distance r, And the B field at this point is mu naught I over 2 pi r. I is the current, mu naught is the constant, r is the distance to the point. Now there is circle is a specific arc. In fact, I'm going to give you the the equation mu naught I over 2r. And that is the B field at the center of a circle. Don't worry, I'm not going to ask you about any other location around that wire. The thing about this, a lot of people ask me, well, if a straight wire is mu naught I over 2 pi r and an arc is mu naught I theta over 4 pi r, where'd the pi go? Why did it disappear? There should be a pi there. It's got a pi in all the other equations. Where did the pi go? It completes it because it what?
I said it completes it, so it doesn't matter, right?
Correct in a way. What's the value of theta for a circle?
2 pi.
2 pi. So this has a 2 pi in it, so it's mu naught I 2 pi over 4 pi r. This is the arc for a circle, and you get that. So technically the pi is in there, but it cancels out with the 2 pi of the theta. These things not to call anybody out, but Alexis, got a question for you. Right hand rule, how good are you at it? Do you know it? It's okay to say, I don't know.
I get, it depends on which one we're talking about, because I get them mixed up.
Okay. What we're going to do first is we're going to do kind of like a brief 15-minute. This homework is still due. Whatever. If you want to take an extra day on problem set 4 or whatever. In Alexis, you're going to learn a new game. This is the right-hand rule game. Now, anybody who has taken my class, they look at this. In fact, it's like, I mean, this is something, in addition to it's a correctly constructed problem, this will be written on my tombstone. This is the typical game that we use for figuring out right-hand rule. Right-hand rule is we do first vector crossed with second vector, and it equals third vector. Now, I understand what's really interesting. All teachers teach things differently. And I heard that Marshall has a first right-hand rule, second right-hand rule, third right-hand rule. I deal with it in a little bit more general situation. And I initially teach it in a general fashion. The first vector, fingers, palm, forearm, all line up. So in this case, A is towards the ceiling in this particular case. Now granted, the students are well aware that if I turn it like this, A is towards the wall, A is now towards the floor. The directions don't really matter. What does matter is in the first vector, fingers, palm, and forearm are all in the same direction. So this is A like this. That's A as written here. Notice how fingers, palm, forearm all in the same direction. The second vector, fingers, not fingers only, point to second direction. So if we have A cross B, A is towards the ceiling, B is towards the wall. Notice how when I go from A to B, the only thing that moves are the four fingers, A to B. The third vector, the thumb points naturally in the direction of the third vector. So the A vector is towards the ceiling, the B vector is towards the wall furthest away from the entrance door, which means that the thumb points towards the back of the room. So, and I only do this because this is my favorite part of the whole writing movie. See, if Amy was here, I would do this, but she's not here, and that makes me sad. You know what? I may have to give. I almost said I was going to give everybody in the room points. But, so, huh? You support that? You know what? Amy, I'm going to have to let you figure out if we did or not. Now, if I had this is my magic bow and arrow. What do you see, or what are you very concerned about with my magic bow and arrow? The arrow hitting you. What do you see when the arrow is aimed at you? The tip of the arrow. This up here, that's the tip. That's the vector coming out of the page. Now, if you were lucky enough, you stole my magic bow and arrow and had it pointed at me, what would you see now?
Are you terrified?
I'd be terrified. Please, I'm sorry. I don't want to. I'm not going to fail you. You would see the fletching, the feather, the back end of the arrow. So that means you see that. E is a vector coming out of the page. Like if I drew a circle with a dot on this table, that's the vector coming out. F is the vector going into the page, which means that the vector is going into the wall. And so that's the big difference between the two. So first vector, fingers, palm, forearm. Second vector, fingers curl in the direction of the second vector, thumb points in the third. Now, for those of you who took 213 in June, you're sitting there going, this is old. In fact, that's a great question. So you're one of my veterans from June. If I was to ask you, and notice how she just she turned on you so quick. If I asked you F cross D, what would you say?
I thought F was down to 4, and then E was to 0.
It doesn't have to be labeled. In fact, the letters could be Chicago, Oxford, Paris. I mean, it could be all sorts of letters. The direction labels don't matter. It's the directions associated with the letters that do.
What do you see?
For F cross D, yes, you would be correct. Now, how did you do that?
I went down, and then I crawled my fingers towards D, and then I went
Very dangerous thing that you just did. Now, it doesn't matter. The way that I have it set up, like this, would be as if you held the page directly in front of you, like this. F, right now, is forward into the page. If I have this on the desk, so what you did is you actually wrote it down, and then F is down there. If I held the paper like this, then F is that way. The important thing to like Alexis and the others who haven't taken it before, you could orient this page any way you want. F is now that way. F is now that way. F is now that way. The critical part of this problem is you don't change the orientation of the page while you're doing the problem. If you go, all right, F is that way, and A is that way, it's not going to work. So for F cross D, let's just all look at the board together. F is this way, right hand only, hence right hand rule. D is that way. Notice how I don't say left, right, up, down. I just say that way, that way, and that way. F. Now notice what I did just then. As long as the arm is all aligned in the same direction, it doesn't matter. Now D is in this direction. And look at the way that my arm is positioned. I can't snap my hand over. There was a girl 5 years ago who sat in the front row. She was double jointed. And she literally took her hand and then she could take her fingers and like you could do this, she could flip it back over her forearm. And I was like, you've been abused as a child. No human can move like that. So, but what I do then, notice what I do, this. I rotate my entire forearm, palm, and fingers all in the same direction. Now I can curl my fingers in the right direction. My thumb points that way. What's that way? C. And that's a brief review on the right hand rule because we got to move on. There is an exercise of the right hand rule in problem set 5, which is due on Friday, and so you can work on it. And I think we do it in the tutorial. But with the right hand rule, I call this my primary right hand rule. When I say right hand rule, it's this. It's the general technique of first vector, second vector, third vector. With these guys, the right way the way we won't do is the Biot-Savart rule. And you could look it up, and the Biot-Savart rule is a way, it's for Cal-based students, we'd be using the Biot-Savart law. The way that the pre-meds, the general physics, the exercise science, all that stuff, we will be using I think Marshall calls it like right hand rule number 5 or something. I mean, he's got a name for it. I call it the wrap rule. Thumb points in direction of current. B field wraps in direction of fingers. And once again, we use the right hand for this. I call it the wrap rule. It gets the job done. If you have a wire I, and you want to know where does the B field go, you put your direction, your thumb in the direction of the current, and see how my fingers come out of the page on the left-hand side. The B field on the left is out. Now, if I continued wrapping my fingers around, the fingers, if I could crack my arm and just have it flop over, the fingers would go into the page on that side. And so we get this. If I had the current going in the opposite direction, the B fields would look like that. So this is for the current going up. This is for the current going down. If you wanted to know left and right, you could just rotate it like that, and then you got it. In a circle, if the current is going counterclockwise, what I do is I think of this segment of wire right here as current that is going directly up, and we see how the current is directly going up here. So we see that it's positive to, or out to the left and into the right. So it is out to the left and into the right. Wire going down is like this: out to the right, into the left. And so it is so for a counterclockwise current, the current is coming out of the page. And if you do the same, or I'm sorry, the B field, and if you do a clockwise current, the B field is going into the page. And so, and you could treat the same thing with arcs. If the arc looks like it would complete a clockwise motion, the center of the arc is into the page. If it is a counterclockwise, the center of the arc is a out of page. In the out of page represents a positive B field. The into the page represents a negative B field. So in the situation where I go, if I was 0.5 amps, what is the B field at a point, and is it into or out of? If that distance was 2 meters. And all you would go is, you would say it's a straight line. So the B field is mu naught I over 2 pi r, mu naught 4 pi times 10 to the negative 7, 0.5, 2 pi, r is 2, and I love stuff canceling. That cancels with that, and I'm left with 5 times 10 to the negative 8 Tesla, or 50 nanotesla for it. Now let's say that we had a wire, 2 amps. We have a circle here. The radius of the circle is 0.5 meters. That distance there is 2 meters. And I want to know, oh, and the current, hold on. The current going through there is counterclockwise with an I of 0.1 amp. And I want to know the B field at that center. Is it into or out of the page? Mm-hmm.
I thought the formula for the B field was 4 pi r on the bottom, not 2 pi r. I could have just written it down wrong.
Mu naught I over 4 pi r is for what geometric shape? Actually, it's for no geometric shape. The 4 pi r is only associated with the arc. Mu naught I theta over 4 pi r for an arc. The straight wire is mu naught I over 2 pi r. In this particular case, we have a circle and a wire. The total B field is the B field of 1 added to the B field of 2. Now, for problems like this, figuring out the B field anywhere other than the center of that circle would require calculus, and we're not going to do that. So if you see a circle or an arc, the B field that we measure has to be at that center. Now, if it was an arrangement of wires and you've got that in the problem set, then we could do all sorts of fun with that. At this particular point, the B field, and that's 1 and that's 2, I1 and I2. B1 is mu naught I over I1 over 2 pi R1. This particular B field at that point from this wire is into the page, because current goes in the direction of the, or thumb is in the direction of the current. B field is out on the left, in on the right. So it's negative. B2, this point is to the left of an upwards current or to the right of a downwards current. So that is positive. So this is positive mu naught I over 2R2. And it's a circle, so there is no pi. I mean, granted, that is depressing to live in a world with no such thing as pi. Sad. You add them together. This becomes minus 4 pi times 10, and actually, well, let's just power through it. I1 is 2 pi. Now, here's the question. What is the value of R1? Is it 2? What's the distance from the wire to the point where we're studying? 2.5. It's 2 meters from here to the edge of the circle and another ½ meter to the point. So it's 2.5. Now this is 4 pi times 10 to the negative 7. I is 0.1. This is 2, and R2 is 0.5 or 1/2. That cancels. And we're left with a lot of stuff. Negative 4 divided by 2.5. This is not an equal, that's a plus. I think, and if people make sure that I'm not doing the math wrong, I get negative 3.4 times 10 to the negative 8 Tesla. So this is 34 nanotesla into the page, is how I would answer it. And so a lot of this is just summing up. The B fields add up. The B field created by one object at one point also experiences a B field from another object at that point. And so we add those B fields together. And so this is just adding up B fields. Now granted, in the Russian review mode of doing physics, we kind of hit the high notes and then we'll fill everything in on the review days. The thing that we do with B fields is, I mean, if you have, really, when you think about magnets are just little hunks of iron where their plane of electrons are all going in a particular direction. And typically for a non-magnetic hunk of iron, all of the orientations of the molecules are going in different directions. Oops. So the net effect is not that much. Because when you think of it a little atom with a little cloud of electrons, those moving electrons are a current, a small current, and that small current will create a B field. If all those B fields are opposing each other, such as this, but not to as an extreme, the net effect is negligible. You can't really feel anything. But if all the particles are aligned, for those rockhounds in the group, we've got it's called the camel's back. One of our astronomy professors was like the Indiana Jones of rocks back in the 1950s and 60s, and he would travel to distant lands and steal stuff. And he would, or actually liberate them to bring them to a museum. And one of them it's the biggest rock on display, and it's called the Camel's Hump. And it comes from a big stinking hunk of meteorite. And when meteorite goes to the atmosphere, it melts, and all of the atoms align a lot of the times in a particular direction. And that hunk of iron out there in the hallway is just super magnetic. And so if you take like little magnets and you could just let go, like he had the thing open, he was setting it up when I walked by. He was like, here, take this magnet and just hold it up to it. It just goes thwack, and then you try to pry that magnet off and it doesn't want to come off. There's an attraction between that meteor and whatever magnet you're trying to put up against it. So now, with these hunks of iron, if you ever, one of the things that we used to do as kids when we wouldn't tell our mom and dad, well, back in the before LCD monitors came out, the monitors were basically these big TV sets where all a TV set is, well, the old ones, not the ones that we have now, is, and this is one of the reasons why they were these big stinking pieces of furniture, is that there was a source of electrons, and there were a series of plates, and they would set up an electric field within the plates, and it would basically steer the electrons, and if the electrons hit a portion of the screen, it would light up. And it's doing it so quickly that it's setting up pictures, because the electrons are basically interacting with this hunk of glass that's coated with a chemical. And to you, it just looks like Howdy Doody or whatever you watch back in the 1970s. Or, well, that's more like 50s. But what my brother and I would do, you couldn't do it a lot, is you would get a magnet and you would stick it up to the TV, and what would happen is that these charged particles would see the magnetic field of the magnet, and you would bend the electrons. And if you held the magnet up close to a TV screen, you would distort the image. And you couldn't do it for long, and you couldn't do it with a strong magnet, otherwise you would mess up the material. But it's an interesting thing. And the other thing about, like, the fun thing about magnetic fields, just to think about it, if you could figure this out, we'll get a Nobel Prize for it. If we have a magnet, the magnets typically have a north end and a south end, and the way that we label the magnetic fields, it looks a lot like the E fields from two charged particles. And if I took a crowbar or a hammer and I cracked that magnet in half, we would end up with two magnets, each with the north end and with the south end. And if I cracked them again, you would end up with the same thing. North, south, north, south, north, south, north, south. Because all it is really It's the material all aligned in a particular direction. With charge, you can have a positive or a negative charge. You can have a negative where the E fields all look like this or like this, all in or all out. It is impossible, as far as we know, to have that. You can't do that because every time you crack a magnet, you still get another north and another south. These are what they call magnetic monopoles. As far as I'm concerned, they don't exist. Theoretical physicists have kind of thought out a way that they could exist. And if these are one of the things where if the person who figures that out will immediately go to Stockholm and pick up a Nobel Prize in physics, if they can figure out magnetic monopoles. But since, as far as I'm concerned, you can't go to Walmart and pick up magnetic monopoles, so it doesn't exist for the moment. I'm not saying that it's impossible, I'm just saying they haven't completed the work yet. So in our little world of 214, it's not happening. If you have a charge, like I said for a charge passing through a magnetic field, and this is where the right-hand rule now comes into play, the magnitude of the force of a charge entering a magnetic field is the charge itself times the velocity times the magnetic field. Multiply those three things together and you got a force. The direction, and I only use this for figuring out directions, F vector equals Q V cross B. So in this particular case, V is towards the top of the screen. V is, V is towards the top. B is into the page, which means the thumb V cross B is to the left. Now this is one of the things that we need to be careful about. If it was a positive charge, it would be the same as a negative charge. V cross B would still be to the left. But the problem with this is, when figuring out the direction, you've got to take into consideration the sign of the particle. For positive particles, the force direction is in the same direction as the V cross B. For negative particles, it's in the opposite direction because the charge is negative. So in the case of the proton, or positive charge, V cross B is to the left, therefore force is to the left. In the case of a negative particle, V cross B is to the left, but it's a negative particle, so you flip it over to the right. So in the event of a positive particle entering a magnetic field that's in, it banks left. It's circular motion. V cross B and a negative of that means that negative particles bank right. If the B field was coming out of the page rather than in, the forces would be flipped. If it was a neutral particle, no force. And why is that? What's the charge of a neutral particle? 0. So 0 times V cross B is 0. So we don't have to worry about that. In circular, and this will be the last thing, we got 4 minutes and I'm not gonna use all of it. In circular motion, and this is where we'll pick up for tomorrow. In circular motion, the sum of the forces, which is equal to ma, because it's circular, is mv squared over r. A is v squared over r, and that is equal to qvb. That force is one of the forces, and the forces have to sum up to ma or v squared over r. One of the v's cancels, and you're left with mv over r is equal to qb. And this is an equation that we're going to use in many different ways, and we're going to do that tomorrow. So, this is the last thing for sure, promise. Grader is pretty much done with the grading. He's going to show up hopefully in the next 10 minutes in my office. Once he gives me the tests, it'll take me about an hour to add them up and record them. So probably those of you in the 3 o'clock lab could probably drop by at 2. Those of you in the 1 o'clock lab, when your lab lets out at 3, come on over and you can pick up your test. The test will be on the table next to the box. I missed you, Amy.